Hi classmates from IOE419 and Professor Daskin. My name is Mark Grum along with Zach Rollin, and we are here to talk about video G6, the applications of the basic equations to the infinite Q. A question you might have is, why would we even bother with talking about an infinite Q? It is not very realistic, and there is no such thing as infinite servers. In some cases this is true, but an infinite Q has certain characteristics that are desired in real-world applications. Two big factors or characteristics that the infinite Q has are the first one being that there is no queue, and the second one being that there is no wait times in the queue, because as noted there are no queues. When picturing an infinite Q, feasibility can be brought into question. There are no such thing as an infinite amount of servers. However, there are certain examples, such as self-service, which resembles an infinite Q. For example, when you read a book, you choose when to turn the pages and continue reading on. As soon as you make the decision to turn the page, you turn the page. There is no waiting time for the service to be completed. The only time in the system is the turning the page, aka the service time. Although certain systems, as mentioned, do not operate with infinite servers, we can and want these systems to operate with little to no wait times, and therefore we approximate them with an infinite Q. Certain examples are ambulances and fire departments. You would not want to have a long queue, and you would not like to have to wait a long time if you were having a cardiac arrest or if your house was on fire. You would like to quickly be served so that you could stop the cardiac arrest and put your house out if it was on fire. Before we begin using the infinite Q, there are a few things to know. First is that the arrivals follow a Poisson process, which means an average arrival rate is given, but since Poisson has a memoryless property, you don't know the exact time of the next arrival. Similarly, services are completed exponentially, and an average service rate is given, but since the exponential distribution also has a memoryless property, you're not sure when, in fact, the next service will be completed. Also, as mentioned, there are an infinite amount of servers, so there is no queue or wait time. Pictured below is a state transition diagram. Arrivals are given as lambda, and services are given by n times mu, depending on how many people are in the system. As shown, state 0 is the state where no one is in the system. State 1 is where one person is in the system and being served. And state 2 is two people being in the system and they are both being served. With more people in the system, as you can see by the increasing service rates, you are more likely to have someone's service be completed, and therefore move down in the state transition diagram. Taking a look are the following state probabilities for the infinite Q. Using lambda and mu, we can compute state probabilities. P naught, also known as the probability of being in state 0, is equal to e raised to the negative lambda divided by mu. And again, this is state 0 where no one is being served and no one was in the system. P sub n equals lambda divided by mu raised to the n power times e to the negative lambda divided by mu, all over n factorial, where n is integers starting from 0 and increasing. As you can see, this is the exact Poisson probability mass function with parameter lambda mu, and n is the state you are currently in. So P1 would be the probability that you are in state 1, and P sub 2 would be the probability you're in state 2.
L is equivalent to the average number of customers in the system. In the infinite Q, L is equal to lambda divided by mu. LQ is equal to the average number of customers waiting to be served. In the infinite Q, LQ is equal to 0 due to the fact that there's an infinite number of servers, and as a result, there's never a wait for a server. W is defined as the average time in the system. In this instance, W is equal to L divided by lambda, which is equivalent to 1 divided by mu. This value is the mean service time. WQ is the average time spent waiting in the queue to be served. It is equal to W minus 1 divided by mu. In the case of the infinite queue, WQ is equal to 0 due to the infinite number of servers. It can be difficult to imagine a practical example of the infinite queue, so we've provided one. Suppose you wish to buy the number 1 rated app in the Apple App Store. How does this situation relate to the infinite queue? Due to its nearly infinite number of users and its self-serve design, the Apple App Store can actually be approximated as an infinite queue. Lambda is equivalent to the arrival rate of customers to the App Store and has a Poisson distribution. The service rate is equal to n multiplied by mu and depends on the user's internet and download speeds. There's no wait in the queue for service because of the self-serve aspect of the App Store. As soon as a user decides to download an app, service begins. In reality, the App Store is not a perfect infinite queue. The server cannot actually handle an infinite number of users, and the web service will crash if overloaded. This scenario, however, is extremely unlikely given the volume of users the App Store typically services. Thank you very much.